Here we go. Okay, so today we're talking about authentication. Very fun. So, authentication systems ensure that secrets are protected and access to protected resources is restricted to people who are authorized to view the actual information. The term authentication is commonly used to describe the aggregate process that governs the operation of authentication systems. Sure, we're all familiar with some sort of authentication, such as entering your password in order to get into your computer. There's three main aspects of authentication systems. Establishing identity. So that would be along the lines of you just simply being like, I'm a person, I'm here, I'm Greg. That's my identity. My identity has been established, right? Verifying that. So now that we know that I'm Greg, we want some sort of way to verify that I'm Greg. Obviously, you could use like a government ID or something like that. You could use your passport. That's a way to verify your identity. And then lastly is authorization. So we know who I am. We know that we have verified who I am, but what am I authorized to view? What am I authorized, am I allowed to go into this place? Yada, yada, yada. Any questions so far? We're doing good? Cool. Okay, so establishing identity. Authentication systems require a unique digital identity for each user. The integrity of authentication system is bounded by type of mechanism used to establish identity. So we want to make sure that the entire system that we're using is all encompassing and establishing the identity in addition to verifying it and authorizing it. So there's four different ways that we can verify or establish our identity. So the first one, signing up for a user account, that would be something like creating a GitHub account, right? You just simply go on, you create a user account, and you're set to go. Can anybody think of what a third-party service might look like as far as exactly? Yeah, that was a good example right there. So instead of signing in with like your actual user account on their website, you just log into Facebook, and then Facebook says, "Hey, this is the person. I promise, let them in. They're a cool guy." And so that would be social integrity using a third-party service. Verifying personal knowledge. Can anybody give me an example of what that might mean?
Like when you log into your bank and they ask you for your social security number, or they're like, what was the name of your first car? And like they save that for later.
Yeah, exactly. It's information that really only you would know. There's no, you don't want to obviously be like, what is the color of stop on a stoplight? Like that's general knowledge. But pertaining to yourself, you want to verify using knowledge that only you personally would have. And then finally, biomarkers is kind of, everybody uses that on a daily basis. The thumbprint scanner on your phone would be considered a biomarker. And of course, the futuristic like eye scanners and everything, that would be biometric because it's literally verifying your identity by using your DNA and your actual body. So that would be a biometric integrity check. Any questions on that before I move on? Good so far? Awesome. So when we're implementing man, I am sorry, guys. I am just like spaghetti mouth today. So when we're implementing authentication systems, the best practices for implementing authentication systems are constantly evolving. And as new systems are put in place, vulnerabilities are discovered and exploited, and then new approaches are invented to protect against those vulnerabilities. So it's a constant cycle. We're not using the same authentication technology that they were using when the web was created. We're constantly evolving these authentication and authorization systems, and there's constantly new iterations coming out to combat the vulnerabilities and exploits that people discover. So obviously, if there's no authentication whatsoever, your server isn't set up for authentication. This is a simple relationship of what that would look like. You'd say HTTP get this file, and then it would be like, here you go. I think it's pretty basic. I think we all get that. For plain text passwords, this obviously is would be a problem if you were going to store your passwords like this in a production level environment, because if somebody was able to gain access to your database, they would have the password of every single user that's ever logged into your website or registered for your website, and obviously that's really bad. So this is definitely not what we want to be doing. This is bad practice. Never do this, essentially. Even plain text on secure channels. I did a little bit of research as far as like what they exactly meant as secure channel. Um, the conclusion I arrived at was that they were talking about HTTPS, which is essentially where before your server, pardon me, before your computer communicates with the server, there's a little handshake that occurs before where the server will send you a hashed string and a number, and then your computer has to run some sort of computation, pardon me. The server will send you a random number and it responds acknowledging that you're there. So then the server will send its certificate saying that it can accept HTTPS requests because it's not default enabled by every single domain. And then you will respond with a hashed message depending upon the random number that you received. And then once the server confirms that the hash is correct after you ran the algorithm with that random number they gave you, then they verify that you are the one that they intend to actually transmit data back and forth between. So in this context, a plain text password, even stored with an HTTPS request, would still be bad because it's not about the necessary connection. It's about where it's being stored and what's being stored. So in this instance, we still don't want to do this because, again, if somebody gained access to our database, it would not be good. So the way HTTPS works is you're essentially signing messages back and forth and encrypting it, making sure that only you and the server necessarily have the access or hashed string to decrypt the messages you're sending back and forth. So that's the difference between HTTP and HTTPS, is that it's hashed, essentially, communication. So it's much harder to intercept. That being said, again, you still don't want to send or save plain text passwords across any sort of connection. So now we're going to talk about encryption. It's a reversible transformation of text into an alternate representation. So this is an example of encryption. Encryption is where we're able to take the base data, such as bicycle, run some operation on it to completely change it, but then expect that we would be able to reverse that operation and get back exactly bicycle in this instance again. So yeah, you can see here we have bicycle, we do it by 2, we get this weird string, and then when we run it against -2, we get bicycle again. So this would be encryption because you can obfuscate the data and then you can gain it back. Any questions on this before I move on? Yep. This would be like on your, it would probably be in your controller before it goes into the connects file or your database. You would want to have this in the controller, and you would have this function declared shift by, and you would have it do, here, let me go forward a little bit. You'd have this function at the bottom, and so you would call that when you want to run the encryption function. Typically, this is not what we want to use because of the fact that it is reversible. You don't want people to be able to go into a database, even though they're not plain text passwords, they know at some level that it's encrypted, and they're going to run a ton of algorithms to try and unencrypt them, and then they'll have the plain text passwords again. So we're actually not going to be doing this either, but just as an example, this is what encryption would look like and what encryption is. That answer your question? Cool. Any other questions before I move on? Awesome. So encrypting passwords, this is what it would look like. This key down here is representing that hashed communication I was talking about before. So we're sending our password correctors with the key. It's encrypting it, and then it's storing it in the database. You know, this is obviously safer than plain text passwords, but this still isn't best practice, and this isn't what we want to be doing. So we're going to be doing hashing. Hashing can be thought of a version of encryption that is lossy. So this means that it destroys some of the information as opposed to encrypting it. So we're actually going to be removing pieces of the original data as we're hashing it. So that way it's not reversible. So that way, if somebody did gain access to our database, they wouldn't be able to run an algorithm to, try and reverse it or try to move it around. It's completely irreversible. That's the intent of hashing. And yeah, there you go. So the original cannot be recovered if you're hashing correctly. Since some of the information is missing, it's not reversible. So yeah, these, I'm sure we're kind of familiar with these. These are hash strings, these long lines of characters that signify the original data, or sometimes it's used as an identifier. You might see those like for API keys and stuff like that. That's what a hash string looks like down there. Any questions? Cool. So hashing a password, we send a secure connection to the server. It takes our password, hashes it, and now we're storing the hashed version of our password in our database. And so this is much safer because it's no longer reversible. So if somebody did gain access to our database, they wouldn't be able to reliably reverse what we did to hash it. And there's different hashing algorithms. The most popular one I've heard is SHA-256. You may have heard that's like SHA-256. There's a bunch of different encryption algorithms though. There's also MD5 and SH1. I mean, there's a lot. So if you really want to dive deep on hashing algorithms, you most certainly can. But just know that there's a bunch of different types and you might be working with different types of hashing algorithms. The most common one at the moment is SHA-256. And so, any questions? Well, we'll get to that. We'll get to that. But to answer that, it essentially makes it so that the hashing algorithm has more so we'll get to this, I promise. But to answer your question really quickly, it's because the longer the string that you input into the hash algorithm, the more complicated it's going to be. And when you're talking about characters, like if you think, if you could only put a password in as integers, like 0 through 9, that gives 10 possible characters that a password could make up. And so the caveat with hashing is that while it's not reversible, it still has one-way data flow. So the way you could force a hash is if you had some very simple strings and characters, and you kept running it through the hashing algorithm to see if it matches with one of the other hash strings that you've seen in like a database or something like that. So when a company asks you to like, please include numerical numbers, please include, special characters, what they're trying to do is broaden the pool of characters that are possible to go into their hashing algorithm. So that way, if they were compromised, it would be significantly harder for somebody to like brute force keep running all of these simple strings into it, because now you've introduced all of these other variables like, the percent symbol, a capital A, a lowercase a, which are considered different characters by computers. But that's essentially why a company or a website would have you do that. Sure.
So, if 10 people all have the same password, it's like they put their password as password. Does that mean the hash password for all of them is going to be the same, or is it different for each?
Yep. That's why we're not only talking about hashing, but that is correct. If you had a SHA-256 hashing algorithm and you typed in Apple, it would generate the exact same string as somebody next to you who typed in Apple as well. So that's why hashing doesn't necessarily solve all of our problems. It certainly helps, but it's not the complete end all be all of what we're going to be doing to authenticate and like obfuscate our data. Does anybody know what a rainbow table is? It sounds really fancy, right? It sounds like, wow, what the heck is that? Unfortunately, all it is just a list of passwords alongside the hashed passwords. So this is something that, hackers will use. They'll grab these rainbow tables and they'll try to run all of the passwords against different hashing algorithms and then store those in a table and then they'll try to use those hash strings to break into your account, depending upon if you're using, like QWERTY. So like if you were logged into example.com and you typed in Superman as your password, somebody could manipulate the server so that you could send an HTTP request saying like, hey, here's my password as the hashed version, and they would be able to log in as yourself because that's what your password is stored as in their table. So rainbow tables are used by hackers, bad people to try and break into accounts. It's like a giant list of passwords alongside, hashing algorithm outcomes and stuff like that. So you can see on the right there, there's like hundreds of millions of entries that they could possibly go through, and then they'll just run a loop to try every single possible string, and that's how they would like brute force into your account if we were only storing our passwords as hashes. Yeah. Any questions on rainbow tables or anything so far? Doing good? Cool. So on and so forth. So salt, this is what is going to fix our problem. In the context of storing passwords, salt is a set of pseudo-random information which is added to a password before it's hashed. Adding salt to a password significantly increases our dataset's resistance to rainbow tables. And we'll see why in the next slide. So this would be the example of a salt right here, and here's our plain text password. And what you'll see with salting modules or functions or algorithms is they're almost always based off of time, because time is constantly changing. That's never going to be the same. You'll more common than not see salting being done based off of the current time. So it's pretty rare to find somebody who just like adds a string onto your plain text password, because then you're running into the same problem where it's like, well, if they got the salt and then they're just concatenating that to all these rainbow table passwords, then you're not fixing the problem. So what you'll see more often than not is salting being done based off the time of the day when you enter it in, and so on and so forth. Does that make sense so far? Everybody following that?
So whenever something gets hashed, is it like first how many characters are equivalent to whatever the salt is, and then the other characters? I don't know how you would store that without, sorry, like not. But I don't
No,
know
you're good. I'm like,
how you would store the correct version of the hash if the salt's always changing.
you store the salt with the actual hash. So like once we're finally done hashing, there's like a reference usually in the first couple characters as to exactly what the algorithm was to salt it. So once you store it as the hash, then it's the first part of the hash is going to be like, hey, this is the salt, and then the later part is the actual hash. So that way, when you're accessing it, it's how do I say this? It's different for every single person, even if you're entering in the same password. So like, for instance, here, if we were going based off of time-based salt, if it was 1 o'clock, correct horse might come out as ABC. But if it was 2, then this might come out as DEF. But at the beginning of the hash, there's always going to be some sort of reference to the salt and the way to unencode it if need be. I don't think that the salting algorithm that we're going to be working with is going to be like reversible in that sense. As a matter of fact, I think the one I'm going to show you actually adds the salt to the beginning of the hash. But salting is essentially how we fix the problem where if you enter an apple into a hashing algorithm, it's always going to output the same thing. Bcrypt. I have an example for you guys after this. I'll show you some bcrypt. But as far as verifying identity, authentication systems verify the supplied identity by comparing it to a previously established identity. So here we have bcrypt compare. We have a password, and then we have the user getting the password. We have our function checking for errors and matches. So we're saying if this matches as far as our hashed password as what, so we're hashing this right here. what the user is inputting, and then in our database, we already have this ready and accessible. So down here, we're checking, okay, is what the user input similar to what we have stored in the table? And so if it does match, we'd say, you know, go next, else kick them back out to the home page. Doing good so far? I have an actual like working example for you guys too after this, so you can get your eyes on and see like exactly what this would look like in an actual program. So there's the supplied password, the established password. So sorry, I had that flipped around. But yes, you can see there we're comparing the two passwords with the hashes using decrypt. That's a module that I'm going to show you guys in addition to JSON Web Tokens in order to effectively obfuscate any user data or passwords. So authorization, this has to do with, you know, previously we were storing it in sessions. We're still going to be doing something similar, but JSON Web Tokens are going to take precedent over that. So with authorization, authentication systems authorize access to protected resources by verifying that the authentication has occurred. So like we've all had experience with this, you know, once the user logs in, you save the session. Once you have the session, you know that they're the authenticated authorized user, and then they can go and, you know, use whatever that they're authorized to use on your application. Authorization middleware, tokens. Tokens are an externally non-identifiable piece of information and can be used in place of a username and password to authenticate a user. A token is delivered to a client via cookie immediately after successful authentication. The server later uses the token to identify and authenticate the user. So this is another like hashed string essentially that will take place of our sessions where the server will check if we actually have that JSON web token in our header, in our HTTP requests header. And if it verifies that we are the person that we say we are, then it will, you know, operate in the expected way. Otherwise, it will kick you out because it's like, hey, this isn't the token I gave you for this user. Why, you know, like, get out of here. I'm done with you. Any questions on that? Doing good?
Does that get saved like in your rules? Like that's what it references?
I tried really hard to figure out where the heck tokens are saved. I even asked Isaac and he didn't know. As far as I can tell, it seems to be saved in like a non-accessible cookie or like a private cookie. So it's still a cookie, it's still a file that your browser is saving, but it's the problem with cookies inherently is that when you go to a website where that cookie is associated, it will your browser will automatically send that cookie no matter what. And there's actually this exploit called cross-site request forgery, where somebody will spoof a website and pretend to be Facebook, and they'll have your browser send a GET request to that spoofed website, and your browser's like, oh, it's Facebook. So it'll send that cookie to that scam site, and then all of a sudden that hacker who intercepted that cookie has access to all of your data. So the reason we don't want to explicitly use public cookies to save sessions is because it can be used essentially to exploit you and reveal your data, because no matter what, your browser will always send a cookie in an HTTP request if it correlates with a website.
So it's a private.
Yeah, it's only meant to be used if it's specifically requested by the website that you're using. I was trying to read up on this as much as I could. It's kind of a point of ignorance for me, but it's stored in a way where it won't be automatically sent to any website that correlates with the cookie. It will only be done when the website says like, hey, I'm looking for this JSON web token, and then you send it in a header to that website. So cookies, we're kind of familiar with cookies. If you're not at that part in the unit, there's a great video in the unit. I forget what block, but it pretty much is like a 4-minute video explaining exactly what cookies are and what they do. It's an awesome video. So if you have the chance, if you skip the video, maybe go back and watch it because it is really good and it helps you understand exactly what a cookie is and what purpose it serves. Uh, that being said, cookies are a way for servers to store information on a client. All cookies for a given host are transmitted back to the server on every subsequent request. Like I said, no matter what, you don't have any choice. Whoa, I didn't know I could do that. So yeah, this would be if you were sending a request or if the server was setting a cookie for you, this is what the response from the server would look like. It'd be like, this is now your cookie, save it, we're going to identify you with it and save all your preferences and all that jazz. So sessions are tokens with an expiry date. I think that's the end of the slide. So I'm not sure if they meant to add more to this, but essentially sessions are meant to expire after a given amount of time. So that way, when you log in again, you have a different session ID, you have a different set hashed string correlating with your actual user. Um, so that way, you're not at risk of, let's say you have a cookie stored on your computer in January. If it never erases itself, maybe you go to some scam website in November and they're going to have access to that cookie. So by constantly saving it and changing it and making sure that it expires after a certain amount of time, that makes sure that you're generating new cookies to be identified with yourself, which helps with security by not constantly having the same exact identifier associated with your computer.
Do they use those on like a lot of websites? Because I feel like the only sessions I'm ever in are like on my bank or like in my insurance.
Yeah, I think even those websites are probably using like tokens. I don't think that like, especially with banks, I can't imagine that they would be using sessions.
It's
Um,
like you have no activity for 20 minutes, like and they kick you out
yeah,
and make you like re-log in. Like,
yeah.
is that what this is, or is it something
Yeah,
else?
exactly. They might, it depends on how they have their server set up. So like, and again, with the expiration date of the token as well, um, if they want it so that like the moment you log out, it expires, and then when you have to log back in, they create a new one, they might have it set up that way. Maybe they have it so like if you click, remember this computer for 30 days, at that point, they would probably save a token that has a lifetime of 30 days. Otherwise, yeah, it's going to regenerate the token, pardon me, the session every time you log in to be identified with you. I said that very sloppily, I apologize, but yeah. So I have a working example for you guys. Let's pull it open. I'll make sure I size this appropriately, and this is going to error out. So I can show you some code here real quick too. I kind of just pieced this together. This is a Frankenstein, so hopefully it still works as I intended to, but it might not. Essentially what I added was decrypt. So here we have a hasher file inside of config. Can everybody see this okay? We good? Cool. Okay. Let me, whoop, that's not what I wanted. Move that down. So this is a module that you can install. You literally just type in npm space I space bcrypt minus node.js, and then you have access to this module. And so this is how you would set it up if you wanted to use it in your application. I can Slack out this file as well as another repository that Troy, our former instructor, had where it was all fleshed out and everything. But I essentially just stole that part and just threw it in here just to show you guys. So you can see that we have salt associated with bcrypt. So the hashing algorithm takes, promise, it generates the salt based off of the integer that we say up here. And then if there's an error, throw the error and reject it. Otherwise, we're going to hash the user password with the salt. I forget what this argument is. And then, of course, the callback, if there's an error, reject it. Otherwise, the user password is going to be hashed now. And then I forget what resolve user does, but I believe that just says we're okay to go, you're set. And so then if you're going to check Essentially what it's doing is we're using that compare again, like we saw in the slides, and we're checking the user password versus the encrypted user password, and then we're checking if it's a match or if it's just going to throw an error. I changed something. There we go. And then one more is JSON web tokens. Where did I put that? Here. So another one, MPMI JSON web token. Pretty much all you need to do is you take this module, you require it in your controller, and then you want to have some sort of secret string for it to like hash based off of. And then down here, you can see I'm calling bcrypt. Let me back up. Up here, I require bcrypt as hasher. And so down here, I'm calling methods on it. That same one that we saw right here, hash. I'm calling hasher.hash on the request body, .then. We're going to insert this new user, .then we're going to send the message successfully registered, please log in, catch the errors, all that jazz. And that's pretty much it. Like bcrypt is meant to be kind of taking, it's meant to take the load of having to encrypt and hash and solve all of your passwords and stuff. It's really, really great. So bcrypt does a lot of the stuff that we just talked about underneath the hood for us to make it a lot easier. And then down here, we can see when I log in, we're checking the email, and then we're using the hasher to check if it's a match. And then if it is, we're going to be creating this token and signing it to the user with our secret, which in this case is just secret. And then we're going to delete the user password. We don't want any reference even hashed inside of our database. So once we confirm that this is the user that we're looking for, we're going to delete the user password. And then we're going to send back the message, we successfully signed in with the token and the user, else throw an error. And yeah, that's all I got for you right there. So let's spin this up and you guys can take a look. Boom. Probably pump that up a little bit. So here I'm going to type in z@z.com with the password is z. I'm going to register, and there is an error because I did not migrate my tables. Pardon me. Of course, it was working before I gave the presentation, and now it's not. Don't know. Register. Well, okay. k@k.com. Okay. There we go. I don't know what the heck happened, but so we can see I successfully logged in. I'm registered, or pardon me, I'm successfully registered and it wants me to log in. It gives me the ID back. But before we go back to log in, let's take a look at our table. You can see here my password is hashed with the salt that bcrypt generated. So obviously this isn't Z, and you can see like just even off of a simple password Z, it takes it takes Z and explodes it into this enormous hash string. And so the salt in this instance, I believe it's in between the money signs, and that's dynamically generated based off the time, like I was saying. So this is our new password essentially, as far as our database is concerned. Yeah. Well, here, I'll do z@z.com, and then I'll do the same password, K. I think I did it as K. Let's see. Sorry, I can't make this bigger. Does anybody know how to pump this up? If I hit, oh, I didn't say that. Never mind. Before it wasn't working. Okay, all right, I'll take it. So yeah, you can see Z at Z, blah, 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 blah. And then right here, you can see that actually the salting is the exact same because we're entering it in at a relatively similar time. It depends on the way that the algorithm is written as far as how often the salt changes. So they might have it based off of the minute, they might have it based off of the hour, they might have it based off of the day. It really depends on how they wrote it. Obviously, they're not going to be willing to explicitly share the entire way it works because then that would make it so that it's vulnerable to attacks. So I have no idea what time frame the salting works off of. I just know that it does work off of time. And then we can do a@pay.com and we'll do Z again. Yeah, so we're still getting the same salt at the beginning. So maybe once the hour changes, let's see.
The two, so the 2A is the version number,
Okay.
and then the 10 is how many passes you did. So if you want to compare, everything after that is salted. It's just that if you wanted to compare two strings, you want to use the same number of passes of the same version.
Awesome.
So we normally like the normal amount of times you salt, like the average is 10. That's what normal.
I read we should do maybe 12 or more. It's up to you.
Or like the standard is 10, but like some places normally like I mean you can do up to like 2,000, but it might take an hour to get your password back.
Yeah, exactly. Yeah. I appreciate that. I actually didn't know that.
So that's why you type in Z for the same password and they don't look the same.
Mhm. There we go. And then to see the actual JSON web token in action, we'll go back. I forget what I did. Z at Z, is it Z? Ah, dang. Did I do K? There we go. Okay, so this kind of looks a little sloppy, but we have our message here successfully signed in with our JSON web token that's going to be associated with us, with the session, with the user, right there. So this is what it's going to look like when you're using tokens and you're instead of sessions, this is what the token is going to look like. So here we have our email. We don't have the password because we don't want to return the password in plain text, obviously. But now we're going to be using this token to associate with z@z.com instead of their password or their session. Because again, a session stored in a cookie will be sent in a GET request no matter what if it corresponds with the website that it's anticipating it to send it to. And so if we go back, everything's the same. I think if we go into sessions, no, okay. Didn't get quite that far. I know that there's a way to see exactly where the JSON token is stored. Didn't get that far in prepping this lecture, but I just wanted to show you guys like the actual implementation of tokens and bcrypt. So I don't know where the token is. I'm sure it's somewhere. But yeah, that's essentially how you would implement these authentication and authorization technologies into your Express.js applications. Very, very simple. Are there any questions over anything I just went over?
I think the part that I'm having trouble understanding is maybe this is the part in the middle here that I don't have to understand. But so say you went to a different browser that didn't have a token in it, and you went to sign in again and you use the same password, and then whenever it gets salted, it comes in as a different string than the string you want to save in your user database as the password. So how does it match this up authenticated and say that you're the same person?
So you're talking about like with bcrypt. how does bcrypt know that the passwords match? Um, it has to do like with what Sean was saying. The way it's stored is it remembers what the salt is for the the actual hash. So since it has this string in the front and it knows how many passes it did with what version, bcrypt will automatically be able to essentially cross-reference it or use the same. I believe it uses the same salt on this on your password, and it checks to make sure that those strings are the same, because the reason that these are here in this way is because we're creating the user at that exact moment. So when we're cross-referencing it and we're checking it again, we're going to enter in the same password, but it's not going to be the same time. So what bcrypt is going to do is it's going to go to this password and be like, okay, how was this salted? And so since it has that salt part at the beginning of it, it's like, okay, let's run this salt with this hash to check to make sure that the passwords match. And so then once it does all of that for you under the hood, then it's like, okay, this user is a real user. He's authenticated, blah, 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 blah. Does that make a little more sense?
So is it kind of moving backwards and then bring the original back?
It's still going one way, but it's just remembering how it salted the hash, essentially. It's not reversing it in any way because it's lossy. There's no way to really get back the original information that you input. So it's just remembering how it's salted what you input to the hash. And so maybe I could write it. So it would be something like you have a password, and then the password gets hashed, um, and then salt. Okay, I'm doing. Let me think. I get what you're asking. Let me figure this out.
Is it because it saved what time it was created at, so it knows what the time is to run with the salt?
I do not believe so. I do believe it specifically operates off of the hash string that it gives you. The salt is stored in there. Like, I don't know, and they're probably not going to tell anybody where or why, but um,
But then how is it that if you have like A and A and Z and Z or whatever, that you typed in the same password and they don't look the same?
um, good question.
So you know how like a pivot table is a list of hashes. So here you have one password and it could have say 100 different hashes. So you're just running the algorithm again and getting that 100, and if it like runs into that same hash over 100 different times, then it knows the password matches.
Yeah, so it's running through every salt, or it's running through every.
It's a solid and it's just running through that whole list of possibilities.
Okay, all right. Thank you, Sean. I appreciate that. Yeah. I don't know a whole lot about what's going on under the hood. I just know that the information is stored with the salt so that it knows how to run the encryption checking based upon your password from months ago and now. It's like when I created this password and I stored it, it was stored with the salting and the hashing. So then it goes back and it's able to be like, okay, yeah, it's I apologize. Yeah. Yeah. Sean, I think explained it a little bit more eloquently than me, but yeah. It's all under the hood. Bcrypt isn't going to release any source code or any other algorithms because if they did, like I said, it would open up vulnerabilities. So um, the way it works entirely, I'm not sure, but I just know that it somehow remembers the salting and it's able to take your password and run it through the hash with the same salt and give you a match if it matches. So I will Slack out the repo where I stole this from, the bcrypt and the JSON web tokens. And then um, Isaac was planning on doing a lecture. I'm not 100% sure. Let me stop this recording.